In this video, we are going to talk about how to check if a linked list has a cycle. How do we know if a linked list has a cycle? Well, first off, we know this linked list has a cycle, and there's a reason we can tell. Our mind is doing something where something is of critical importance and we're paying attention to it. So where do our eyes go when we look at this problem? This is an approach we can use for many problems to convert kind of how we look at things into actual procedure. Well, we immediately see a bunch over here and we know there's a cycle, but we're gonna probably scan the list a bit until we see all of this. And then we're gonna see there's a 4, and then we do a bunch of looping, but then we come back to the same node. How can we make this into a procedure? Well, we're keeping track of the nodes that already happened somehow. And if we go back to a node that already happened, which is the definition of a cycle, then we're going to know that the linked list has a cycle. So that gives us our first method. We can just use a set of sorts. A set, which is just going to keep a set of the unique memory addresses of each object in memory. If we go back to that same reference, we're going to know we just cycled back if we've already seen it. So that's our first approach. We can actually just go straight into implementing it now. It'd be linear space and linear in time. So let's go see that. Okay, so we have our function signature. And first off, what can we do? Create our set that we're going to keep track of items we've seen. We see the same cycle in depth first search, breadth first search. We're going to use a set of sorts to prevent retraversing nodes we've already seen. Let's create our set. Okay, that's our set. And now remember, linked list problem. We have a head. Let's put a working pointer on him. And then we're going to use that to iterate. And now we can create a while loop. While this working pointer is still alive, continue looping. And then we just do a simple if statement. If I've already seen this node, then return true. There is a cycle. And then if that checks out, if everything's fine, then we're going to mark the node as seen, advance iteration. If the whole iteration ends and we haven't backtracked to a node we've already seen, we're just going to return false. There's no cycle. All right, so this is what we did. Created a hash set. We put a reference variable, iteration. If we've seen it, return we do have a cycle true. If not, we mark it as seen. Advance to the next. Cur becomes its next memory address. And then we keep looping. When cur's null, that means no cycle. We return false. So this first approach is linear in space. It's also linear in time. It's linear in space because in the worst case, the list has no cycle. And then we have a set full of all unique nodes, which there'd be n nodes. And that bounds to linear space. And then for the time, we're going to, again, in the worst case, do the whole list. And ultimately, our upper bound is linear for both space and time. So now let's look at how we can actually optimize to constant space and linear time. But this is kind of a more niche thing. I heard that this is something that was discovered after years of like research and proving or something. And I don't know why it's an interview thing, but it's one of those subroutines you need to know for linked lists because it actually proves useful for other problems. Let's look at it right now. So I'd like to teach the intuition behind this, but I don't really think there is an intuition because it's not something you would just know. You would have to be familiar with linked list manipulations to know this. But you're going to use 2 pointers. You're going to use a fast pointer and a slow pointer. Okay, so how does this iteration go? We're going to move the fast pointer forward 2, slow pointer forward 1. Let's do 1 iteration. And ultimately, our goal is when these guys meet, that's when we know there's a cycle. And there's probably a proof behind this. Again, this is not something you'd intuitively know. If I did have to give an intuition, because the fast pointer is moving an even amount, and the slow pointer is moving an odd amount, something's going to happen over at the cycle. And then you'll see it, and then I'll show you. So move the fast forward 2, slow forward 1. That's where we're sitting. 1 more iteration. And then let's do another iteration. And then let's do another one. And then 1 final one. Okay, both of these guys met. And I guess the intuition I could give is that because the fast is moving an even amount, the slow is moving an odd amount. When they do, if this did not have a cycle, the fast pointer would just be gone. It'd go to the end of the list, finish the list, and then the slow pointer would have nothing to do. It'd just be sitting here. But if there is a cycle, what's going to happen is these guys will be trapped. This cycle will absorb both of these pointers. So they're going to just go cycle, cycle, cycle. And if one is moving an even amount and one is moving an odd amount, eventually they're going to meet. And the reasoning is, let's count out numbers. Let's both start at 1. And the top's going to be fast, bottom is slow. So let's advance forward 1 iteration. Let's move forward another iteration. And now I want you to imagine at the number 7, the cycle starts. At the number 7, a cycle starts and now these nodes are going to be absorbed within it. So let's just continue iteration, and let's imagine that 7 is the head of the cycle and 10. 10 is the node that comes back to 7. So it would look like this. So it's 7, and then there's going to be nodes in between. We know it's 8, 9, and then the 10. And then the 10 points back to 7. So let's continue with this counting, starting from cycle entry. The fast is at 7, the slow is at 3. Now let's move forward one iteration. The fast can go to 9. That's still within this cycle. The slow is going to go to 4. And let's actually make this concrete just so it's really easy to follow. And then let's move forward again. We're going to move the slow to 5, and then the fast is going to come back to 7. And then move one more forward. We're going to move this to 6. And then the fast is going to go to 7, 8, 9. And then we move the slow to 7. And then the fast starts at 9, 10, 7. And we see that as soon as slow entered the cycle, in fact, fast met it. And this is what I mean by absorption. As soon as these nodes get absorbed into the cycle, they're just going to be playing within the cycle, and eventually they will meet. Again, I don't really know whether this has an intuition. I literally just thought of this right now. I guess this is the best intuition, that once they're trapped, they're just going to play with each other in the cycle and eventually meet because of how they're iterating. So now, we know there's a cycle. We return true. This is pretty simple. We could just set up 2 pointers, iterate them, while fast does not equal null, or while fast.next does not equal null, something like that in the while loop. We're going to continue. If the while loop breaks out, no cycle. So pretty straightforward. This is a pretty common subroutine as well. There's other uses for this, like if you want to find the middle of a linked list. If you're not allowed to get the length of the list, you can use the same approach of fast and slow pointers. You start a fast and slow pointer, advance it forward, and then advance again. And then when fast is null, or when its next is null, we stop, and we know that the slow pointer is at the middle. And this is another really common linked list subroutine, but I just wanted you to know that because this has more uses than just this case. So how do we find the start of the cycle? The start of the cycle is right there at 4. Now for the solution, I think the best way to explain this is to show this with a picture to explain the intuition. It's best explained that way. So first off, we're going to find the length of the cycle. And again, just stay with me. This is going to make sense as we do this. We're going to find the length of the cycle. We can move either pointer forward. We're going to use the slow pointer to find the length. So let's put the length to 0. Now we move the slow pointer forward 1. And we're going to keep doing this because we know we're sitting in a cycle. It's just going to cycle back. As soon as it hits the fast pointer again, then we know that we found the length of the cycle. We've gone through all of it. And now it move S forward again, and then one more time. So the length of the cycle is 5. We just got the length of that inner cycle right there. And we're just going to keep this over here. So now our pointers are right where they started because we just got the length of the cycle. We want to find what is the head of the cycle. And I want you to imagine this image. So how would I find the head of this sublist? So imagine we want this node. Well, if I know the length of the sublist, I can create a window, and I can keep track of the start of the window and the end of the window. So that's what I ultimately want. I want where that head is pointing. And what I can do is, if I know the length of the window, I can start the window at the start, and then I can iterate it forward until this goes to the end of the list, until tails next is null, or however we do this. We're going to keep iterating this window forward. So the window is size 4, so by the time I hit the end of the list, I'm going to get what I wanted here because of the nature of how we're doing it. So let's iterate forward. So that's iterating forward, keeping the length intact again. That's it again. And then let's iterate 2 more times. And then when that node's next is null, then we found the head of that sublist. Because we want the head of the sublist at the end. And we know the length of it, but we don't know what that node is. We just create a window of that length. So we're going to do the same thing here, and let's just do it first, and then it's going to make a lot of sense when you see the picture. So we're going to keep a left and right of the window. And then the right pointer is going to go forward 5 positions. So we're going to say right go forward 1 time, and then 1 more time, and then again, and then a 4th time forward, and then again forward. So what does this create? This creates a window the size of the cycle. And ultimately, we're going to try to lasso around the cycle, and the head of this window that's going to wrap it is going to be the left and right. When these guys meet, that means we've wrapped the cycle. And how do we know this will wrap the cycle? It's because it's the exact length of the cycle. So if we continue iterating this forward, when left and right meet, that means we have wrapped the whole cycle, and wherever we met, that is the head of the cycle. Because when these two guys meet, they're going to have met at the region in which the cycle begins, where it loops back to itself. So let's continue, and this is going to become clear. So advance both pointers forward one time. So that's one iteration. Now let's iterate again. And that's another iteration, and you're starting to see where this is going. So let's do one more iteration. And now L and R have overlapped, and we have wrapped the cycle. So we just return either of those. Those are the head of the cycle. So this is how you find a cycle in a linked list, whether a linked list has a cycle, and you can find the head of the cycle. Find the length of the cycle, create a window, advance that window until the edges of the window meet. Then the cycle has been kind of lassoed or wrapped around, and these two items will be at the head of the cycle. So this was finding a cycle in a linked list, and this is going to run in linear time and constant space. We're not creating auxiliary space, it's all pointers and a linear time, because at worst, this has no cycle, and we're just going to do a fast pointer all the way to the end. We do n over 2 iterations, or roughly that, and that's just a fractional component of the length of the list. So we stay to linear time. And this is finding a cycle in a linked list.